Now screen is visible.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. I guess some network issue are there. That's why. Okay. So now it is clear. My voice is already clear, right? So today we will be having a basic introduction to battery pack design. How what things we consider while designing a battery pack. Okay. What parameters we consider. So those all things we will be discussing about. Okay.
Yes.
Okay. So first thing, like to have a design of battery pack, first thing we need to sell a battery, right? We need to select a cell. Okay. To design a battery pack, we need to select a cell. But earlier I told you we have firstly we do have the vehicle. Then once we have a overall, we have a basic idea of the weight of the vehicle, right? On the base of that weight of the vehicle, we decide the capacity of motor required, right? So we discuss about motor as well. We, how this motor, we will be calculating the torque required by a motor to propel that vehicle, right? So in last class, we already have been discussed about that. Once we have that motor capability, then we do have requirement of motor. This motor requires this much of power, right? And then depending upon range, see whatever electric vehicle you have to make, you will be having some range. Okay, in one charge by management, or you can decide in one charge, in a single charge, my vehicle should go 200 kilometer or 300 kilometer, like that, right? So on the basis of that, you can be having a overall battery capacity. And now you have to design a battery pack. And while designing a battery pack, first thing you need to do, you need to select a cell. Okay. So form wise, three types of cells are there: cylindrical cell, prismatic cell, and pouch cell, right? So
Yes.
form wise,
Yes, sir.
we do have three types of cell: cylindrical cell, prismatic cell, pouch cell. So depending upon the space requirement, you select one of the cells. But what usually happen, all the cells have some pros and cons, right? So cylindrical cells, they comes in higher energy density. Okay. The plus point is with cylindrical cells are, you know, in any space, whether this is triangular space, there is a trapezoidal space, whether it is a circular space, in any kind of space, you can be able to fit the cylindrical cells, right? But in case of this prismatic cells and pouch cell, they are also good. In these kind of cells, what is the benefit? The cylindrical cells comes in fixed dimension, and that is, what, that is in some standard dimensions are there. For example, 18650. Okay, so that means the 18 mm diameter and 65 mm height. 21700, that means 21 mm diameter, 70 mm height. This 41680, that means, sorry, 4680, that means 46 mm 4860 means 48 mm diameter and 60 mm height. So these four standard dimensions are there. In those only the cylindrical cells used to come. But in case of prismatic cell and pouch cell, energy, in terms of energy density, they are having less energy density compared to cylindrical cells. But this comes, in a customized dimension. Whatever dimension you wish, you can ask your manufacturer, and they can be able to provide you the cells in that dimensions. Okay, so that is the plus point of that this prismatic cells. Okay, and the pouch cells as well. So once you decide which kind of form factor you are going with, whether you are going with the cylindrical cell, whether you are going with the prismatic cell, whether you are going with the pouch cell, then you decide the chemistry of the cell. What you decide? Chemistry of the cell. So in chemistry of the cell, although here is a list, all those cells are lithium ion cells, but in lithium ion cells also with different chemistries are there. Like for example, LCO, that is lithium, cobalt, and oxygen based chemistry, and that is used in cell phones, cobalt rich and expensive. These all cells are very expensive. That's why they are mostly used in cell phones and the laptops. Okay. Then comes NMC, that is very popular cells nowadays worldwide, mostly used cells in case of the lithium ion chemistry. that is called nickel, manganese, and cobalt. Nickel, manganese, and cobalt based chemistry. So one thing is common for each and every cell. Graphite is common, that is anode. But the chemistry, other chemistries are changed. And so this kind of cells, NMC is mostly used in electric vehicles. NMC 811 has minimal cobalt, nickel rich version attempts every smaller cobalt, even a smaller cobalt. NCA. So this is something similar to NMC, but this is having lesser energy density and lesser price. So whenever you are not able to afford NMC, okay, NMC cells are very costly. So when you are not able to afford NMC, then you will be going with, and you can go with the NCA cells. Okay, so this is similar to NMC, less expensive, lower number of cycle used by Tesla as its battery size is large. Then it comes LFP, lithium ferrous phosphate. Okay, so this is I guess 5 or 10 years back, this kind of chemistry was mostly used in electric vehicle industry, and that was most popular chemistry. But nowadays, due to limited specific energy, limited energy density, that cell are not preferred nowadays in the industry. But it is safer than NMC, limited by specific energy, used to be dominant in China. This chemistry especially have been developed in China, and they were using mostly. And whatever the companies who were depending upon China to import the cells, they were mostly using prior. But nowadays, this kind of chemistry is on the way to obsolete. Then another NMC cell is there, which is having the anode as a LTO. LTO node gives much longer life cycle and temperature tolerance, safe but poor specific energy and high cost. So this kind of cells, which is having LTO as a anode, they are, you know, uh, the temperature tolerance is high. Nowadays you might be aware about that. Few electric vehicles have been caught the fire, right? So those all terms of reasons are there. But if you try to avoid this kind of thing, because the lithium ion cells are very sensitive to heat, right? So once the temperature has been raised, so this event is called thermal runaway. I already explained about that. When a lithium ion cell reach some specific energy level, then it explodes, right? Or some temperature level, then it explodes and high fire causes, right? So that event is called this thermal runaway. Okay, so that event could be happen. So in this type of cell, LTO and all, they are very having the high temperature tolerance and not that much sensitive to heat compared to NMC and NCA. So these are this kind of cells are somewhat safer than other cells. Then again, we do have LFP as a LTO as a node. So this is also similar to NMC LTO. Okay, so this kind of most used this lithium ion based cells are there, and with the different chemistry. So depending upon different application, you can be able to choose your cells, right? So if I summarize this, if you are having the high energy density requirement, you can go for NMC cell. If you are having the high energy density requirement, but cost is also a matter for you, then you can go for NMC, which is having slightly lesser energy density and slightly lower cost. Okay, so again, if you want to, okay, completely safe battery packs which are no more sensitive to heat and all, but those all kinds of cells will be having very lesser energy density, then you can select the LFP, right? Then again, if you wish to have a high power cell, okay, and longer life cycle, and temperature wise also you need a more range. Okay, the range of the cell operating, the range of the cell in the temperature, you need more temperature range. Then you can select the NMC and LTO based chemistry. NMC cathode wise and anode wise LTO chemistry you can select. Okay, so you have been decide about the form of the cell. So this is the first parameter. Then you can select the chemistry of the cell. That is the second parameter, right?
Yes.
Then what we looks for in a battery. So once we are designing a battery, what you are looking for in a battery pack. Okay, So first thing is there. So to having a electric vehicle. So in electric vehicle, what you require? You require top speed. You require top, good range. Okay, in 1 kilometer, in one single charge might be you are requiring for a longer range, right? Like 400 kilometer or 500 kilometer or 300 kilometer, right? People are demanding like that. Okay. So what happened? In order to achieve a longer range, okay, so you should have high energy. Once you have good energy level, then only, see, for example, uh, okay, very simple example. You have a normal conventional vehicle. For example, you do have a bike, right? You have a bike, and it is giving a mileage of 30 kilometer per hour. For example, there is a sport bike and it is giving a mileage of 30 kilometer per hour. Okay. So in order to achieve 300 kilometer in a single fuel tank, you need a 10 kilometer fuel tank, right? Sorry, 10 liter of fuel tank, right? Similarly, in order to achieve, for example, 390 kilometer, okay, 390 kilometer of range in a single fuel tank, you will be required a 13 liter fuel tank, right? So you are increasing the capacity of the fuel tank. Similarly here, if you need for a longer range, you have to increase the capacity of the battery. Okay. Now, greater you increase the capacity of the battery pack size and weight will increase, right? And if you have a lower specific energy of the cell, then more size and more weight you require. That's why in order to have a great, in order to have a good amount of range, you need a higher kilowatt hour capacity of the battery pack. And in order to achieve a higher kilowatt hour of battery pack in a lesser area, in a compact area, you need a higher specific energy, right? And that's why you need to build a battery with higher ampere hour. Okay, understood? Why high specific energy is required. Now second term is high specific power. So now consider a point ki, battery, whenever you are drawing a current, whenever you are running your electric vehicle, that vehicle runs on motor, and motors demand some current. Okay, motor demands some current, and that current comes from the battery pack, correct? And that battery pack sends current each and every cell manufacturer having some limitation. You can draw or send a current maximum in this rate, right? So higher the specific power, higher the draw of rate of drawing the current would be. Okay. So batteries made for power tools and electric powertrain provide high load capability, but the specific energy is low. Okay. So whenever you need a higher, current demand, you have a higher current demand, you need a higher specific power. But we do have some constraint. If you go for a higher specific energy, the higher specific power will get lower, and if you demand for a higher specific power, the higher specific energy, the specific energy will get reduced. So this is something we are not able to overcome till now. So people are working on the different chemistry to do it affordable price. Obviously, in especially if you talk about India, Indian market is very case sensitive to price, right? So each and everything people here are looking for the in a affordable price range, right? So materials, refining process, manufacturing, quality control, and sale matching, these all add the manufacturing cost, right? So volume production, if you produce any part in a lesser volume, your cost will be high. Same part, if you produce in a higher volume, this price will get reduced, right? So you have to work on the manufacturing cost. So we are looking for a battery which is having the affordable price, long life. So obviously, you know, you need a battery pack which is having a longer life. It should not be you invest 10 to 15 lakhs in an electric car and your battery pack get obsolete in 3 4 years. In an electric car, the 50% price around on and around 50% of the price of the vehicle contributed by the battery pack itself. So you don't want to lose your 50% of value in a 3 to 4 years, right? So the longer life should be there. Okay. Safety. So this is very concerning point nowadays in our country. Safety. The battery should be safe. You heard about lot of cases in recent days about the fire happening in the electric vehicles, especially in two-wheelers, right? So high specific energy are often reactive and unstable. Okay, and when used correctly, brand name lithium ion is very safe. People nowadays telling you, okay, the electric vehicles are not safe, the lithium ion batteries are not safe. This is nothing. When you are using those in a correct manner, when your design is correct, then this electric vehicle, the lithium ion is very safe. But some people are there who, you know, uh, in terms of earning money and all, they are not taking care about good design. They are not taking care about good batteries and all. And so those vehicles are, those batteries are not safe. But if you are going to design a battery pack, obviously should be your utmost priority. Your battery pack should be safe, right? Wide
Yes, sir.
opening, wide opening range. Here I do mean ki this battery pack should be able to run on lower temperature and as well as higher temperature. Okay. So cold temperature slows the electrochemical reaction of all the batteries. Lithium ion cannot be charged below freezing. High heat shortens battery life and compromises safety. So these all kind of things should not be happen. You as a customer, as a designer, you should be able to design such kind of battery pack which didn't have this kind of impact, right? So in a battery pack, wide opening range should be there. If it is a lower temperature like Kashmir and all, there also this battery pack should work. And if it is a higher temperatures, for example, Jaisalmer or some other Churu and similar tropical area in Rajasthan, it should be work, right? So there should be a wide opening range in terms of battery pack design. Toxicity. The battery pack should not be toxic, right? The emission, the suppose when you are, you know, once your battery pack life have been ended, and then you will be discarding that battery pack. And while discarding, obviously it will get for the it should be in a manner it should get recycled and minimum to minimum toxic material should get produced. Not only while the discarding, while assembly, while manufacturing also the battery pack should not emit the toxic materials and all. Okay. So nickel and lithium based batteries contain little toxic material, but they still pose a hazard if disposed carelessly. So there should be a mm, strong or tough rule should be there to dispose the battery packs. Okay. Fast charging. Obviously, we can't wait. Suppose your battery pack is having 400-kilometer range, and you are on a long long tour, and suppose you take a rest. Okay, for example, after 200 or 300 kilometer, you take a short break. Okay, in that much of time, your battery pack should get at least 50-60% charge, so that in next stoppage you could be able to charge your battery pack again, right? So fast charging provision should be there in your battery pack. So lithium battery should be charged at 1C or slower. Fast charge possible only if batteries are built for it. Be in good condition at room temperature. Aged and mismatched cell hurt during fast charging. Okay, so these all points you should take care about to design a battery pack. So how many points I told you? I told you some parameters like a specific energy, a specific power, affordable price, long life, the safety, the wide opening range, the toxicity, and the fast charging. So these are all parameters you should take care about when you are designing a battery pack, because these all are points a customer looks for. Okay. So now moving ahead in terms of battery pack design. So a basic design of battery pack looks something like this. So this is a exploded view of a battery pack. You can see there are cells. Okay, these all are cells. In bottom and top there are cell holders are there. Okay, and once the cell holders are there, then the side packaging are there, the gray one, or you can say the black one. The side packagings are there. Then at topmost you have the separator. You can see this is a separator, and onto that some bus bars are there. You can see this gray color, the steel gray color. This is the bus bars are there. Okay, and then you have a final connection. These 2 points, these two bus bar is a final plus and minus to connect with this electronic board, and that is called BMS for the battery pack. That is called battery management system. And then you have a top and bottom enclosure for a battery pack. So a typical battery pack looks something like this. Okay. Now I will be going with the battery calculations, basic calculation of the battery pack. Okay. So what usually happen? So I decided the cell. Okay. I decided the cell. Okay. And I decided the the chemistry of the battery pack. Okay. Chemistry of the cell. I consider all those fine. Now I have to start the design of the battery pack. Okay. So I have some basic calculation. But before doing that, you should know some battery basic terminology, which will be helpful for you to do the calculation. One is nominal voltage. Nominal voltage is something what on that cell, each and every cell, some nominal voltage is rated there. Okay, that is the average of the maximum and minimum voltage. Maximum voltage is the maximum voltage which that cell could be achieved. The capacity of the battery pack, what around amount of capacity in that cell is having, in terms that we calculate in terms of age. Okay, for example, you do have the mobile phones and all, and you do have 5000 mAh battery. So if you remove that M, then that will be coming 5Ah, right? 5000 mAh means 5000 milliampere hour. So that would be 5Ah, right? 5. So cells usually comes in 4Ah, 5Ah, 4.2Ah, 4.8Ah. These all are this is for the cylindrical cells. For the prismatic cells, this capacity could be 40Ah, 60Ah, 80Ah. So cells come in different capacity. C rate is something, the rate at which you draw the current or supply the current to the battery or the cell, right? That is the C rate. Current is the flow of electron is called current. Internal resistance, each and every cell is having some internal resistance, and that is the major region which produce the heat in that battery pack. Heat generator, the heat is generated inside a cell due to this internal resistance. SOC is the state of charge, how much the battery pack is charged. That is called a state of charge of that battery pack. Okay, whether it is 20% charge, 40% charge, 30% charge, or 100% charge, that is the called state of charge of that battery. Okay, so once we do have, then we will be doing the some P and S configuration, parallel and series configuration of the battery pack. Okay, so that we will learn now. So I am giving an example. Okay, suppose for example, so whenever you have to decide if you have to make a battery pack. Okay, so what will be you will be having, you will be having some uh, you know requirement. You need to you need some inputs to design anything. You need some input. Okay, so suppose for example, I have to make a 350-volt system. What I have to do, I have to make a free 350-volt system. Okay, and then just a moment. So we have to make a 350-volt system, and suppose I have to make a 200 Ah capacity. I should have the 200 Ah capacity. Okay. So these two requirements I do have. Okay. Whether by the brainstorming, whether from the management, these inputs come. You have to make a battery pack. This should be having a operating voltage of 350 volt terminal voltage, and it should be having a 200 Ah capacity, right? And you have to decide a cell. So we suppose, for example, I have been decided a cylindrical cell. Okay. So that cylindrical cell, suppose for example, I am going with the 31700 cylindrical cell. Okay. I do have this cylindrical cell. Okay. And then I do have that cell, each and every cell. When you are going to purchase any cell, then what will be happening? The cell manufacturer will provide you some input. So I do have the nominal voltage. Okay. Nominal voltage, and that is, suppose for example, 3.6, okay, volts. Generally the lithium ion battery cells is having this voltage, and I do have the capacity of the battery pack. Capacity of the battery pack is suppose 4.8. Okay. So I do have this basic requirement. You have to make a battery pack which should be having 350 volts and 200 Ah capacity. Okay. And I have selected one cell that is having 3.6 volts nominal voltage, and the capacity is 4.8 Ah. Now I have to calculate the parallel and series combination of that battery pack. Okay. Now a uh, funda is there. When you are adding a cell in series, the voltage will rise up. Okay, you know all those. And when we are adding the cells in the parallel, the capacity will be adding up. Okay. So I told you. So we do have the requirement of the battery pack, and that is 350 volts and 200 Ah capacity. And we selected a cell which is having the nominal voltage of 3.6 volt and capacity is having 4.8 Ah. I told you, whenever you are adding the cells in series, the voltage will be adding upon, and when you are adding the cells in parallel, the capacity would be adding upon, right? So I have to achieve 200 Ah, right? I have to achieve 200 Ah capacity by adding this much 4.8 Ah capacity in each and every cell individual. So what you will be doing in parallel, in in parallel, I will be having 200 divided by 4.8. Okay, and this will give me, let me open my calculator, 200 divided by 4.8. So this is 41.6. So 41.6 is not a exact number. So I will be keeping as a 42. This much of cells, because 41.6 cells can't be happened, right? So 42 cells would be there in parallel. Okay, understood, students?
Yes, sir.
Okay. Now in series, I told you the number of cells in series will be adding upon voltage. So I have to achieve 350 volts, right? So 350 divided by the nominal voltage is 3.6, and that would give me, yeah, let me open my calculator. That would give me 350 divided by 3.6, and that is 97.2. So again 97.2 something, what we, the not a whole number. So I would be considering 98 cells in series. Okay. So I can say the generally we write as M P N S. This is the basic writing formulation, that is called M number of cells in parallel and N numbers of cells in series. So I could write 42P and 98S. Okay. So this is my parallel and series combination for my battery pack. Okay.
Yes, sir.
This would be
Yes.
my parallel and series combination for my battery pack. Understood? Any confusion?
No, sir.
Okay. Now moving ahead. So what we have done? So we have decided the form of the cell, we have decided the chemistry of the cell, we have considered a few parameters while designing a cell, we consider the specific energy, we consider the specific power, we consider the pricing, we consider the life cycle of the battery pack, we consider the safety of the battery pack, we consider the opening range of the battery pack, we consider the toxicity level while designing a battery pack, we consider the fast charging methodology in a battery pack. And then we have calculated the battery pack, and depending upon the requirement, for example, I do have the requirement of 350 volt and 200 Ah capacity, and as per the our calculation we calculated that we will be requiring 42 cells in parallel and 98 cells in series, right? Yeah, 42 cells in parallel and 98 cells in series. Okay, so this we have been done. Now we will start the CAD modeling. Okay. So initially what you will be doing, you will be starting with the cell tray, or you can say cell holder. Okay. You need something to stack up the cell. Okay. To hold the cell, you need something which can be able to hold the cell. So this is, some ready-made cell holders are there which are available into the market. Okay. These are some ready-made cell holders for your DIY purpose. Do it yourself. DIY, do it yourself. So for your DIY projects and all, you can be able to purchase this kind of cell holder from the market, and you could, you can see like this, you can insert the cell into this kind of cell holder. So these cell holders are made something like that, so they can be, fixed with each other in this manner. Okay, so this is something ready-made cell holders is there. Okay, if I talk about a basic design of the cell, complete cell module. So I told you in my previous classes. So we stacks the cell to make a module. Okay, we stacks the cell to make a module. We stacks the module to make a battery pack. Okay, so here this is one of the module. So you can this is a tub kind of cell tray is there. Okay, some kind of cell tray is there, and into that you can be able to see this cell holder. Okay, and this cell holder you can see there is a cooling tubes are there. Okay, the springtime kind of cooling tubes are there. In that, the cooling these cells, we will be putting up the cells into that, and then again top side cell holders is there, and then there is a separator, and then onto the top of the that we do have the bus bar, and that bus bar will be fixing upon that, and then onto the top we have a top, you can say top cover or top structure, whatever you can say, you can nomenclature, no, rename it as per your convenience. Okay, so if I say about the another, that is for the cylindrical cell. For the prismatic cell, you can go with this kind of cell tray. So this is a complete big rectangular cell tray is there, and into that for cooling purpose, I have some circular holes are there. You can be able to see, right, and then you can see one, two, three, four cells in a row, and in sorry, four cells in a row. Okay, and similarly, four columns are there. One, two, three, four columns are there, and those cells have been connected with this bus bar. You can be able to see this silver color bus bars is there. You can, is it visual to you?
Yes, sir.
Okay. Yes. So and here you can be take out the final connections. Okay. So this kind, depending upon the cell form factor of the cell, whether it is the prismatic cell, whether it is the pouch cell, whether it is the cylindrical cell, you can design, you can make a architecture. You can think in your mind and you can design accordingly. Okay. Just a moment. So this is about the big battery packs. In a small battery packs, what you have done to make a small cell block, cell module, you can say, and put into the battery into this kind of casing. This is for the two-wheelers and all. Okay. So this is some basic designs of the. Okay. So now I will give you a small glimpse of this battery design. How we design a small battery pack for the into the CAD. Okay. So first we have the, suppose for example we are going with this cylindrical cell. So first I do have the cell. Okay. Then I would arrange the cell. Okay, like this. Okay, so there could be a n number of way to arrange the cell. Okay, for example, these cells are arranged in this manner. You can start arranging the other cell from here itself, but in that you will be leaving long gaps, right? So I have the an ordered in this so that I could be utilizing more space. Okay, so depending upon your philosophy, you can arrange the cells as per you. Okay, the arrangements of cells is there. I have the cooling tubes. Okay, so I will be stacking the cells onto this cooling tube. Okay. Between this cell and the cooling tube, some adhesive would be there that is called thermal adhesive or thermal pad, which will help to stack the cell with the tube and will help us to transfer the heat from the cell to the cooling tube easily. Okay. So these all are cells with the cooling tubes. Okay. Then finally, we will be arranging all those cells and cooling tube like this. Okay. Then I will have the base plate. Okay. Suppose I have designed like this kind of base plate. Okay. So I am showing you an example. This is my way to design. Anybody can design as per them. It should only comply with the compliances. Okay. The battery pack should be followed by the compliances. Whatever the governing authority is there. For example, in India we have the ARAI, right? So your battery pack should pass the homologation rules and all. That's all you require, right? Your battery pack should be durable to comply with the against the compliances, and that is the best way to design a battery pack. So you do have the base plate. So we'll be doing the cell and tubes of assembly with the base plate. Okay. So here also in bottom you could apply some adhesive, and that could be some structural adhesive to hold this cell on bottom, right? Then side packaging is there. Okay, you can see there are some cutouts. Okay, as per the shape of the cell to again to give the cells extra, you can say the holding area and low space requirement. Then here also in sidewards also, since this is made up of plastic. Okay, so all the cooling activity is performed by the this aluminum cooling tube. So here also inside also you can apply some structural adhesive. So in sideward also, in downward also, you have strong holding. Okay, and in between these all have been stuck by the thermal adhesive as well, right? Then you will be doing some top cover. You can say, you can see there is a slots. Okay, these slots Why these slots are there, I will telling you. So once this top cover is there, then you can place the bus bar. Okay, you do have some different kinds of bus bar could be there. This I made very basic kind of bus bar to just make you to understand, right? So this bus bars are there. Now you can do spot welding. In case of a spot welding, you have to keep this bus bar on this cells itself. And if you are willing to do this wire bonding, then it would be in little bit side of the cell, so that the wire will be bonding here and it will be touching here. So how actual wire bonding looks like? So wire bonding looks something like this. Okay. So for example, all my red is positive and blue is negative, right? So I am connecting this bus bar. I am using this bus bar, this particular bus bar to collect the positive, right? So I am collecting all those positive, 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 positive in this bus bar. And so again, I do have this different bus bar. I am collecting all this negative here. Okay. So the bus bar is the, for my understanding, bus bar is the best technology to bond the battery packs and all. Okay. Then you can have a final top cover and your battery pack is fully packed, right? So this is a design basic for understanding how to design a battery pack. Okay. If you have some software in your college, you can try there to design a battery pack. If you are stuck in somewhere, you can reach me. I will be helping you to make uh, the battery packs in a better way. Might be I will be helping you to design the battery pack in a better way, right? So this is just only for the, you can say, for your understanding. See how you basically how you could design a battery pack. Okay. If you see the cross section view of the battery pack, you can say these are cells are there, cooling tubes are there, again the cells are there, and in between this cell and the cooling tube, I will be having the thermal pad or thermal adhesive here. Okay. Similarly, here also this between the cell and the cooling tube, I will be having the thermal adhesive or the thermal pad here. On to bottom of the day, I will be having some strong structural adhesive to hold the battery packs. Okay. On to top of the also, I would be having some. Finally, what we do before doing this, before doing the top cover, okay, once we completed the wire bonding or the any kind, we in these gaps are there, right? So these gaps should not be there. So to the thermal runaway event is very dangerous. So suppose in a worst case scenario, in a bad condition, one cell achieve the thermal runaway. Okay, one cell happen achieve the thermal runaway event, it should not propagate with others, right? To avoid that, we can fill all the gaps by the encapsulant. What is that? Encapsulant, or you can say potting material, that is very insulative by thermal. Sorry, that is thermally very insulative, and electrically also they are very dielectric. So that is kind of acts as a barrier between two cells. Okay. So basically that you know separates those two cells. They once any cells achieve the thermal runaway event, the heat and all should not get transferred or propagate to other cells. Okay. So in the battery pack design, apart from your mechanical structure, some chemicals are there who are playing a major role to design a battery pack, and those chemicals are structural adhesive, thermal adhesives, and sealants. Okay. Just a minute. So first one, the structural adhesive. So structural adhesive we ideally use when we have to adhere the plastic parts with the cells, or plastic parts with the plastics. Okay, so for plastic to plastic, addition, we use the structural adhesive, or for plastic to cell addition, we use the structural adhesive. When it comes to cell to cooling tubes, then we use the thermal adhesive. When you have to make a like top cover and bottom cover. So there you can use the sealant so that it could properly get sealed, and no particulate matter, no water, no air could get, no dust could get into the battery pack. And for that, sealant is very required. In order to make a battery pack, in order to comply with the compliances, we have to make the battery which should be rated IP67 or IP68. Okay, so that is the roles of the adhesive. Encapsulants are there, I told you. So in those gaps between these two cells, we fill the encapsulant. Encapsulants are some dielectric or dielectric and thermally insulative materials are there, which we use to power into that, and that's why they are called potting material as well. Okay, so those all are encapsulants. Sometimes people use PCM material as well. So this is PCM is called phase change material. So how this works? This works on the principle of changing the phase by absorbing the heat. So for example, I am giving a simple example. You do have a ice, right? And the temperature of the ice is 0 degrees Celsius. Normally, when you apply the heat to any body, the temperature of that body increases, right? When you apply the heat to a body, the temperature of that body used to get increased. Correct?
Yes.
Now, in case of ice, if you apply the heat to the ice and if the temperature is 0 degrees Celsius, it will not increase until unless the ice will get converted into water. Okay. Once the complete ice get converted into water, then only the temperature of the water start increasing. Okay. And that heat which that ice has been consumed to convert its age, convert its phase from ice to water, from solid to liquid, from one phase to another phase. That heat is called latent heat. Okay. So similarly, these materials are some, this PCM are some specific material at particular temperature, like they used to absorb the heat. Okay, till the point it could not, it get converted into the liquid phase. Till that point they are absorbing the heat. Okay, so that the battery the temperature of the cell are at nominal. Okay, and that's the PCM material. There are some cooling tubes. The patterns are there. Different cooling tube patterns are there. These are this serpentine cooling tubes are there. This is some, this base cooling plates are there. So you can use different concept of the cooling plates or cooling tubes depending upon your design. Okay, and finally you have a overall battery pack design like this. You can see these modules are there. So that module I showed you, right? This is one module, right? So similarly, this module you can arrange the modules, stack up the modules, and then put into the higher side structures and all. The top and out bottom casings are there. Then the final connections are there, and for that electrical connections are there. Okay, so that will complete the battery pack. If you consider, if I tell you the basic, components of the battery pack, you have some upper part housing, the cell modules are there, battery housings is there, base plate with cooling systems is there, underbody protection is there, battery management system is there. This is very important part. This is the black one. The connected strips are there. Okay, the high voltage connectors are there, and cell management controllers are there. So these all are some basic components of your battery pack. If I talk about some basic production process of the battery pack, okay, I will tell you very simple, because in detail I will be talking in next class in detail the production of the battery pack. Here I will be just introducing a small concept how we usually produce the battery. So initially once you selected the cell, you do the cell capacity test, you do the cell voltage test, that is called OCV test, open circuit voltage test. Okay, then you do the cell internal resistance test. This is called cell selection and sorting. What is called cell selection and sorting. This is very important. Cell selection is important. Once you selected the cell, the manufacturer will send a lot of cell to you. In that lot, you have to sort the cell. Might be there some cells could be there which are damaged, which are not as per the benchmark. So these cells could be damaged. If you use those cells into your battery pack, that could be a reason to be a thermal runaway. That could be a reason for the fire hazard which are happening in the industry nowadays. Okay, so cell sorting is very important. So these three major process is there to sort the cell. Okay, once you have sorted out the cells, then the damaged one you could be separated out. The good one only you will be using. It will be battery pack combination. You will be connecting the BMS. You will be doing it the aging test. You will be potting the encapsulant or potting material. You will be packing, keeping this into the casing. That is the final production, and you will be doing the final packaging. Okay, so that is the that's all from my side for today.